Settle now into whatever holds you. Let your breathing lengthen a little, and imagine you have all the long hours of the night before you, with nothing waiting on the far side of them to be hurried toward. Tonight we will spend our slow, unhurried hours in the company of something you have known your entire life, something so utterly ordinary that you have almost certainly never once paused to wonder at how remarkable it truly is. It is water, plain and clear and endlessly familiar, the very substance you drink and wash in and watch falling from the sky, and by almost any measure the most common and unremarkable thing on all of Earth. More of our planet is covered by it than left dry, its great oceans wrapping the world in blue so completely that seen from far out in space, our home looks less like land than like a single glimmering drop. And it fills you as well, making up far more of your body than you might ever guess, moving through your blood and your cells and your very breath, so that in some real and simple sense you are mostly water yourself. So it is a curious thing, is it not, that something so close to you and so constant should carry a hidden secret within it, and stranger still that almost no one who meets it every day ever pauses to notice. Here is that secret, offered without any alarm or ceremony. Water, for all of its everyday plainness, calmly disobeys very nearly every rule that a well-behaved liquid is supposed to follow. By the ordinary laws of chemistry, a molecule this small and light ought to be a thin, restless gas, boiling away long before any warm afternoon, never lingering as the pools and rivers you have always known. Again and again it turns the expected order of things upside down, behaving in ways that would seem frankly impossible were they not sitting there in the glass beside you and drumming on your roof through the rain each night. None of this is magic, and none of it is the least bit mystical. It is simply real, dependable physics, plainly astonishing when you look, and hiding all the while in the most unremarkable corner of your own kitchen. Perhaps the most wondrous part of it all is this: had water turned out to be an obedient, well-behaved liquid like any other, the earth would very likely be barren, and you would not be here to wonder about it. The rivers would not run, the seas would freeze into solid ice from the bottom upward, and the intricate chemistry that allows living things to exist would have found nowhere in which to begin. Because water bends these rules so faithfully instead, warmth is stored across the seasons, the oceans stay liquid year upon year, and the world remains mild enough for forests to rise and for the small warm animal that is you. Over the long hours that lie ahead of us, we will wander through these many wonders one by one, in no hurry whatsoever, letting each small marvel arrive, unfold itself, and then fade away into the deepening hush of your sleep. There is nothing here you are asked to remember, no lesson to hold on to, no single thread you must keep following. You may listen closely if you like, or let the words blur and run together, whichever suits your tired mind better tonight. Each idea in these hours has been laid out to sit easily upon a tired and heavy mind, one simple thought resting beneath one clear image, and asking nothing of you in return for its company. And if you happen to fall asleep somewhere in the middle of it all, that is entirely as it should be, for these hours are meant as a gift to carry you gently downward, never to hold you awake. So let your shoulders soften now. Let the whole long day loosen its hold on you at last, and come along with me into the strange and familiar world of water, where the most ordinary thing of all becomes a marvel. Imagine for a moment a single molecule of water, far too small for any eye or microscope to ever see, and yet built from just 3 atoms joined together in the simplest arrangement that chemistry allows. At its heart sits a single oxygen atom, the larger and heavier of the trio, and clinging closely to it are 2 much smaller hydrogen atoms, one on either side, like a pair of tiny companions that never let go. You might naturally expect those 3 atoms to line up neatly in a straight row, the oxygen sitting in the middle with one hydrogen reaching directly outward from each end, balanced and symmetrical. Nature, however, chooses a rather different shape, folding the 2 hydrogens toward the same side of the oxygen, so that the molecule bends into a wide open V instead of stretching out as a straight and even line. The angle of that gentle bend measures close to 104.5 degrees, a little wider than the square corner of a right angle, and the molecule holds that shape with remarkable steadiness. Picture 2 arms lifted from your shoulders and spread into a broad, welcoming openness, and you already hold in mind something very close to the geometry that every single water molecule keeps. This bent form matters far more than it might first appear, because within the molecule something subtle and important is unfolding among the small electrons that bind the 3 atoms together. Oxygen is a rather greedy sort of atom, pulling the shared electrons far more strongly toward its own side of the bond than the 2 lighter hydrogen atoms can ever match. Because those electrons slip a little closer to the oxygen and linger there, that end of the molecule takes on a faint negative charge, a mere whisper of extra electric weight gathered at one side. Meanwhile, the 2 hydrogen tips, left slightly starved of the electrons they once shared more evenly, carry the exact opposite hint, a small positive charge glowing faintly at the far ends of the open V. So a single molecule comes to hold 2 opposite natures within itself, negative along the oxygen shoulder and positive out at the hydrogen tips, faintly unbalanced from one end all the way to the other. Scientists give this lopsidedness a name, calling it polarity, meaning simply that the molecule has one positive side and one negative side, much like the 2 opposing poles of a minute bar magnet. Had the molecule been built as a straight line instead, those 2 opposing pulls would have balanced out and canceled each other completely, and water would have remained a rather bland, forgettable, chemically unremarkable little thing. Because of the bend, though, those charges can never fully cancel, and so each molecule steps out into the world already leaning to one side, already reaching outward, already faintly electric across every surface it presents. From this single feature alone, this soft asymmetry no wider than one molecule across, nearly every strange and wonderful habit of water that you will meet in the chapters ahead begins slowly to unfold. Its ability to cling to itself, to climb through the narrowest of spaces, to dissolve so many things, and to hold warmth against the cold. All of it traces directly back to this lopsided, slightly bent, three-atom shape. Think of it as a kind of seed, endlessly repeated across every drop and river and wandering cloud on Earth, each tiny copy carrying the very same wide angle and the very same faint imbalance of charge. Hold that picture of the small bent molecule gently in mind as we go on, for everything that lies ahead in these hours is really just this one tiny lopsided shape, told over and over and over again. Recall how oxygen pulls the shared electrons closer to itself, leaving its own side faintly negative, while the two hydrogens, robbed of a little of their charge, are left faintly positive, a molecule gently lopsided from one end to the other. That small imbalance turns out to be the whole secret, because opposite charges attract, and the positive hydrogen jutting from one molecule feels the steady pull of a negative oxygen resting on a neighbor close beside it. When that attraction takes hold between them, we call it a hydrogen bond, a fleeting handclasp between neighbors that reaches across the tiny gap separating one molecule from the next, joining them for the briefest of moments. Picture each little molecule reaching out with both of its hydrogens toward the oxygens of the others around it, and offering its own oxygen as a handhold in return, so that everything ends up linked to everything nearby. Now, a single one of these bonds on its own is remarkably weak, many times feebler than the strong covalent bonds that hold each molecule's own oxygen and its two hydrogens so tightly together inside. Something like a 10th or a 20th as strong, in fact, a bond so faint that the ordinary thermal jostling of the molecules alone can shake it apart in a fraction of a second. Yet where one such bond is fragile, the whole multitude of them together is mighty, since every molecule in a glass of water clasps several of its neighbors at once, all of them holding hands in every direction. Multiplied across the countless molecules in even a single mouthful, those flimsy handholds add up into something genuinely formidable, a vast and invisible web of attraction threading its way through every drop of water you have ever held. Nothing about this web ever sits still, though, for the bonds are forever breaking and forming again, each molecule releasing one partner only to reach out and take hold of another an instant later. Trillions of these bonds break and reform every second inside, even a thimbleful of water, a ceaseless shimmer of connection and release so impossibly fast that no eye or instrument could ever manage to follow it. Imagine a great crowd forever changing partners in a dance, each clasp of hands lasting only a single moment, and yet the crowd as a whole never quite letting go, always somehow joined together. This restless holding on is the reason liquid water clings so to itself rather than flying apart into vapor, its molecules plainly reluctant to part company for good, even as they endlessly swap their grips. Nearly every strange thing that water does, in the many chapters still ahead of us tonight, can be traced back to these fleeting handholds and the surprising collective strength they lend to the whole. Its stubborn refusal to boil away in the sun, its knack for holding great reserves of warmth, its surface pulled taut enough to carry a small insect, all of it begins with this humble tug between molecules. Even the way ice floats upon its own liquid, so unlike almost every other frozen thing on Earth, is written directly into how these bonds hold the molecules apart, a wonder we will come to in its own good time. For now, simply hold the picture of it steady in your mind, a positive hydrogen leaning toward a negative oxygen, over and over without end, an entire ocean woven from that one small and endlessly repeated preference. There is something reassuring in the very idea of it, that such vast strength can be built up entirely from bonds far too weak to last, the whole held aloft by nothing more than their sheer uncountable number. So as you lie there, picture the water within you and all around you laced through with these unseen handholds, forming and loosening, without any beginning and without any end. By every fair expectation of chemistry, a molecule as tiny and lightweight as water ought to be a thin wisp of vapor, floating away into the air rather than lingering as the cool liquid you drink and wash in and swim within. Chemists often sort substances partly by the weight of their molecules, and as a rule the lighter ones boil away at lower temperatures, slipping into the air while their heavier relatives cling together as liquids across a far wider span of warmth. Consider water's near relatives, the molecules built from the same column of the periodic table, where an atom of sulfur or selenium stands in the very place that oxygen occupies at the heart of a water molecule. Hydrogen sulfide, that faint rotten egg gas, actually weighs more than water, and yet it turns to vapor far below the freezing point of ice, becoming a gas at around 60 degrees below zero on the Celsius scale. Follow the tidy downward trend those heavier cousins trace, and you would confidently predict that water should boil somewhere near 80 degrees below zero, existing on Earth only as a thin and invisible haze forever suspended in the atmosphere. Picture for a moment what such a world would actually hold. No rivers winding through valleys, no rain gathering on the leaves, no oceans anywhere, only a parched and rocky planet wrapped in a permanent shroud of steam. Yet the water resting in the glass beside you tonight remains stubbornly, wonderfully liquid, refusing the very fate that its small size and modest weight would otherwise seem to demand of it so plainly. What overturns that confident prediction is the invisible grip you met a little earlier, the hydrogen bonds that reach out between one molecule and the next, like countless small hands linking across the tiny gaps. Each little bent molecule tugs on all of its neighbors through these bonds so that before any one of them can break free and fly off as vapor, it must first tear itself loose from the whole embracing crowd that holds it. Because so much additional energy is required to sever all of those bonds at once, water clings tightly to itself and holds on to its liquid state across a broad and generous range of everyday temperature. The temperature at which water finally surrenders and boils climbs all the way up to 100 degrees Celsius at sea level, an astonishing height for a molecule so very modest in its mass. Its freezing point, too, sits far higher than the simple trend of weight would ever place it, so that the ice which finally forms is a rare and reluctant surrender rather than the easy early one you might expect. Line water up in a row beside its chemical cousins, and this gap yawns astonishingly wide, very nearly 200 degrees of separation between where the simple rule says it should boil and where it truly does. That single anomaly, born entirely from bonds far too faint for any eye to see, is the very reason oceans can exist and pool across nearly 3/4 of the surface of our turning world. Rivers can wind toward the sea, springs can rise from the ground, and rain can fall upon the fields, all because those hidden handholds keep water gathered and liquid throughout the mild temperatures a living planet allows. Life, as far as we have ever understood it, needs some liquid medium within which its intricate chemistry can slowly unfold, and water offers precisely that across the very range of temperatures where the world stays mild and kind. Think of it, if you like, as a small and steady act of defiance, a humble substance calmly ignoring the very rule its own weight seems to right, and in that refusal giving the whole earth its familiar shade of blue. So as the night deepens around you, remember that the sea itself is possible only because these tiny, lightweight molecules hold one another so faithfully, refusing together the long pull that would carry them up into the empty sky. Among all the ordinary substances around you, water carries a rare talent for resisting change, drinking in an abundance of heat while its own temperature climbs only a little, warming with a reluctance almost nothing else can match. Pour energy into a pot of water on the stove, and much of it does not immediately race the molecules faster, but instead goes to work loosening and stretching the countless tiny hydrogen bonds that tie one molecule to the next. Those little handholds between molecules must first be pulled apart before the warmth can truly quicken their motion, so a great store of heat sinks in and seems to vanish, swallowed into the invisible web without any rise you could feel. Scientists give this hidden capacity a name. Specific heat and water's is remarkably high, about 4.2 joules for every gram warmed a single degree, higher than almost any common liquid you could ever name. Because of that generous capacity, warming a whole body of water takes an extraordinary amount of energy, and cooling it down again means that same great store of energy must slowly and unhurriedly leave. Picture a summer afternoon pouring its sunlight down onto a lake, and notice how the surface stays cool and welcoming to the hand long after the sand along the shore has grown too hot for bare feet to bear. Sand and bare stone heat swiftly under that same sun and lose their warmth just as fast once it sets, while the water beside them is barely nudged, its temperature stirring only by the smallest measure. Through the long months of summer, seas and lakes gather heat without any fuss, storing it deep within their vast volume like an enormous, unhurried reservoir that fills a little further with every passing day. When autumn tips toward winter and the air overhead turns cold, that stored summer warmth begins to seep back out from the depths, released a little at a time across the long, darkening months ahead. This slow give and take is the reason a town set beside the ocean rarely swings toward the harsh extremes of heat and cold that grip a place lying far inland at the very same latitude. Coastal air stays milder through January and cooler through July, cradled by the great body of water offshore that simply refuses to change its own temperature in any kind of hurry. On the scale of the whole planet, the oceans act as an immense buffer against change, smoothing the difference between blazing days and freezing nights into a range mild enough for the living world to bear. Without this steadying hand held over the climate, temperatures would lurch far more wildly between sunrise and darkness, and swing more violently still between one turning season and the next. The very same property is at work within you as well, for your body is roughly 2/3 water, and that inner sea resists any sudden shift in warmth exactly as the great oceans outside do. A sudden burst of effort or a passing wave of cold does not send your temperature tumbling or soaring, because the water you are so largely made of absorbs the change into itself and holds you near steady. Consider how much comfort can live inside a single plain fact that a substance so common and so easily overlooked should turn out to be such a faithful and unwavering keeper of warmth. Every molecule doing this is following nothing more than plain, dependable physics, energy flowing first into the stretching of bonds and only afterward into motion. The same small exchange repeated across countless uncounted trillions. Carry that picture with you toward sleep. The great seas breathing their gathered warmth back into the winter night, and the water within your own body keeping its long, even, and unbroken calm. Nearly every substance on Earth grows heavier and contracts as it cools into a solid, its particles drawing steadily closer together until they pack more tightly in the frozen state than they ever managed while still flowing as a liquid. Water, almost alone among the everyday things you know, chooses the opposite path as it freezes, and in that single small act of rebellion lies one of the loveliest and most consequential secrets of the whole familiar world. As liquid water cools toward its freezing point, the restless molecules begin reaching for one another through their hydrogen bonds, each one settling into a link with exactly 4 neighbors in a deliberate, roomy, wide-open arrangement. Rather than crowding ever closer, those bonds hold the molecules firmly apart, building an open crystalline lattice threaded with tiny six-sided rooms and pockets of empty space woven directly into the very architecture of the ice. Because of all that built-in room, a solid block of ice takes up noticeably more space than the water it froze from, spreading the very same number of molecules across a slightly larger and more generously spaced frame. The result is that ice ends up roughly a tenth less dense than the liquid lying beneath it, and that faint lightness is exactly what allows a newly frozen sheet to ride buoyant upon the surface instead of sinking. Picture the last thin skin of ice forming across a winter pond at dusk, floating there like a pale, translucent lid laid over the water, rather than sinking away and vanishing into the darker depths below. That floating habit, so utterly ordinary to our eyes that we scarcely remark on it, is in truth genuinely strange, since almost any other liquid, once frozen, would drop straight to the bottom like a dead weight of stone. When a lake gives up its warmth to the cold night air, the chilled water at the very top, now lighter than the rest, stays there and freezes, forming a crust across the surface rather than along the floor. From that first fragile film, the ice slowly thickens downward layer upon layer as winter deepens, always building from the surface toward the deep, never once creeping upward from the bottom the other way around. Beneath this frozen roof, the sheltered water stays liquid and dark and comparatively warm, insulated by the ice itself from the biting, relentless cold that goes on pressing down out of the sky above all winter long. Under such a lid, fish glide freely through the unfrozen water below. Insects and frogs wait out the long season in the mud, and countless small lives simply carry on until the returning spring sun melts the ceiling away. Now imagine, just for a moment, a stranger world in which ice behaved like nearly everything else and sank the very instant it formed, dropping away from the water's face the moment the first crystals appeared. In that colder version of things, each frozen sheet would tumble helplessly to the bottom the moment it appeared, and ponds would build up thick from below, layer stacking on layer until they froze into utterly solid blocks. Whole lakes could turn to ice from the floor upward, leaving nothing liquid at all for the creatures trapped within them, and each returning winter would slowly scour living things from the frozen water almost entirely. So the whole living winter that survives beneath a frozen surface rests entirely on a difference you could so easily overlook, a mere tenth of density tucked away inside the open, roomy shape of a single ice crystal. Hold that thin sheet of ice in your mind for a moment, poised across the water and holding the whole hard season at bay, while beneath it an entire hidden world continues its slow, unhurried business through the dark. Every frozen lake you have ever walked beside was, without any fuss or announcement, keeping its own dark depths alive, a floating roof of hydrogen bonds standing guard over the very water it was made from. Here lies one of water's loveliest contradictions, for it grows heaviest not at the very moment it freezes, but a few degrees above that, reaching its greatest density at around 4 degrees Celsius, just short of turning to ice. Cool most liquids, and they simply keep contracting, growing denser with every degree lost all the way down. Yet water breaks from that habit near the end, beginning to swell outward once more in the final few degrees before it hardens into ice. Picture a wide lake as autumn deepens around it, its darkening surface losing warmth to the cool night air, while the whole great body of water gradually surrenders the heat it gathered through the long days of summer. As the topmost layer chills toward that pivotal 4 degrees, it grows denser than the water lying beneath it, and so it sinks, sliding down into the darker depths while warmer, lighter water rises gently to take its place. This slow exchange repeats itself again and again, layer trading places with layer, until the entire lake has settled into one even coolness, nearly all of it hovering close to that heaviest temperature of 4 degrees. Something more remarkable happens once the surface cools further still, dropping below 4 degrees on its journey toward freezing, because from that point onward the very coldest water becomes lighter than what surrounds it rather than heavier. Instead of sinking as it did before, this near-freezing water now drifts upward and lingers along the top, where it meets the chill of the air overhead and hardens first into a thin, fragile roof of ice. Beneath that forming roof, the densest water has already gathered far below at the bottom, pooling in the deep like a hidden reservoir held steady near 4 degrees through all the long, dark months of winter. Consider what this quiet arrangement means for the creatures below, the fish and the insects, and the slumbering frogs who pass the whole frozen season in a cellar of liquid water that never once dips down to freezing. Were water an ordinary, well-behaved substance, the coldest water of all would simply sink to the bottom, and lakes would freeze steadily from the floor upward, turning every winter pond into a solid and lifeless block of ice. Because of this single reversal near 4 degrees, ice can only form as a lid across the very top, sealing the gathered warmth below and letting the living things beneath wait out the bitter cold in a sheltered dark. Notice how the entire life-saving arrangement depends on nothing grander than a handful of degrees of temperature deciding, moment by moment, which parcel of water shall be light and which shall be heavy enough to sink. When spring at last returns and the sheet of ice melts away, the surface water warms steadily back toward 4 degrees, grows dense once more, and sinks again, setting the layers of the whole lake into motion all over. This seasonal stirring carries a name among those who spend their lives studying lakes, who call it the turnover, a slow and thorough overturning that visits many lakes twice in every year, once in spring and once in autumn. As the heavy surface water descends through the depths, it carries dissolved oxygen drawn from the air down into the lightless deep, where fish and countless smaller lives have been waiting through the season for that renewing breath. Rising up in exchange comes water grown rich with the nutrients that had long settled to the bottom, lifting them back toward the sunlit shallows above, where tiny green living things can feed upon them and grow. In this unhurried way, a lake renews itself without any effort or intention of its own, its whole volume gently rinsed and refreshed twice a year by the very same odd density that keeps its winters survivable. Let this image stay with you into sleep. A deep lake breathing deeply once in the spring and once in the fall, its whole hidden world held alive by nothing more than 4 small degrees of difference. Deep inside a glass of water, every single molecule is tugged outward in all directions at once, surrounded on all sides by neighbors who pull upon it with equal and opposite force. Right at the surface, though, something shifts because there are no water molecules drifting in the thin air just above to reach down and pull upward on that topmost row. Each molecule stranded up there feels the strong inward and sideways tug of its companions below, yet finds nothing at all to balance it from the side that faces the open sky. Left unbalanced in this way, the entire surface draws itself inward and pulls taut, coming to behave like a thin elastic sheet stretched snugly across the very top of the water. Scientists call this surface tension, and while water carries one of the strongest such skins among the common liquids around us, a few others, mercury chief among them, pull tighter still. You may once have watched a small insect stand upon the face of a pond without ever breaking through, its slender feet resting on that unseen film instead of slipping below. A water strider does precisely this, pressing the surface into tiny, dimpled hollows beneath each of its legs, held up by little more than the cohesive pull of that living skin. Consider, too, the way a falling raindrop rounds itself into a small clear bead, as though an invisible hand were drawing the water inward toward its center from every direction at once. A sphere is the shape that wraps the greatest volume within the smallest possible surface, so tension coaxes each free-floating droplet toward that roundest, most economical form it can find. On a waxy leaf or a well-polished tabletop, spilled water gathers itself up into little glistening domes and rounded beads rather than spreading out flat across the surface beneath it. Where water meets the inner wall of a narrow drinking glass, its edge climbs upward into a shallow curving crescent that chemists have long since chosen to call the meniscus. That upward curl appears because the water clings to the glass along the rim, while its own surface skin bridges smoothly across the middle, sagging just a little in the center. Behind all of these small wonders lies the same cause we have met before in earlier chapters, the hydrogen bonds that loosely link each water molecule to the ones surrounding it. Each of these bonds is a mere 10th or 20th the strength of the covalent bonds within a molecule, and they break and reform in trillionths of a second over and over. try to pull the skin apart, and those countless little bonds resist the parting, drawing the water back into itself and mending the broken film almost the very instant it is torn. Picture a steel needle laid flat upon still water, floating there not because the metal is light, for it is not, but because the taut surface simply refuses to let it sink. In every one of these moments, from a bead of dew to a standing insect, you're watching the outermost molecules of water link hands across the open boundary they share with air. Carry with you then this single picture as the night deepens, a silver skin drawn tight over every pond and glass, upheld by the smallest and most fleeting of invisible bonds. Among all the quiet talents of water, one of the loveliest is its knack for rising, for moving upward through the very narrowest of spaces as though gravity had loosened its grip for a moment and let the liquid wander free. Two forces working together make this possible: a partnership of opposites, cohesion, the way water molecules cling faithfully to one another, and adhesion, the way those very same molecules cling instead to the solid surfaces they happen to touch. Inside a very thin tube, adhesion coaxes the water to grip the walls and creep steadily upward, while cohesion keeps the rest of the liquid roped to that rising rim, so the whole slender column is drawn along behind it. This upward reach carries a name of its own capillary action, and once your eye has learned to catch it, you begin to notice its unassuming handiwork almost everywhere you happen to look. Dip just the corner of a paper towel into a small spill, and watch the wetness spread upward against gravity, darkening the dry fibers a good way above the shallow pool where it first began. The very same climb unfolds when the hanging edge of a cloth dips into water, and the dampness travels inward and upward, wicking through the countless tiny channels woven between its crossing threads. Rest a cube of sugar on a wet saucer, and within moments moisture will creep up into it, filling the little gaps between the crystals one by one until the whole cube glistens through. Notice how the thinner the space, the higher the water manages to climb, because a narrower channel offers adhesion far more wall to grip against the modest weight of liquid it must haul upward. Wider tubes let the water rise only a little way, while the very finest passages can draw it upward by a genuinely surprising distance, held aloft there by nothing more than molecules clinging to molecules. Nowhere does this humble little trick grow more astonishing than in the tallest of trees, where water must somehow travel all the way from the cool soil to the sunlit leaves waving far overhead. Threaded up through the trunk run slender vessels, each one narrower than a single hair, and through these countless fine channels the pull of cohesion carries a long, unbroken thread of water steadily skyward. As the leaves release their moisture into the surrounding air, they gently tug on the water waiting below, and because each molecule holds fast to the next in line, the entire column rises to follow. Picture a towering redwood lifting its daily drink a full 100 meters up into the sky, a great raising of considerable weight accomplished by nothing but clinging molecules and the slow evaporation from its leaves. No machinery hums away inside that living trunk. No piston rises or falls. No engine labors in the dark. Only the tireless partnership of countless molecules holding hands the whole way from root to crown. Consider for a moment the sheer tonnage of water forever ascending through the forests of the world, drawn upward without haste and without any notice, hour after unremarked hour, through every trunk and slender stem. The same taut inward pull that draws the water ever higher is the very togetherness that rounds a droplet into a bead and stretches a skin across a pond. Only here it has been turned to the work of lifting. In the soil beneath our feet, this same rising is at work as well, drawing moisture upward from below toward the thirsty roots, threading between the packed grains of earth through spaces almost too small to imagine. So as the night deepens around you, hold in mind the water climbing without a sound through every stem and leaf and root, rising steadily against the whole pull of the world, with no pump and no motor to help it. Imagine you have wandered, at the close of the evening, down to the edge of a small pool that lies flat and dark beneath an open sky, its water waiting there as though it had been expecting you all along. No wind stirs its surface tonight, so the water holds itself perfectly level, a black mirror laid flat across the ground with nothing to trouble it, no ripple, no tremor, only an even and unbroken calm. Above you, a scattering of stars leans down over the water, and each one finds its twin waiting below, doubled in the polished stillness at your feet until the pool seems to hold a whole second sky. Let your shoulders loosen a little as you stand here at the bank, breathing in the cool night air that gathers close where earth and water meet, carrying the faint green scent of reeds and damp ground. Everything you have learned so far about this strange and shape-shifting substance is gathered here in the pool before you, resting now within its dark expanse, asking nothing of your attention and holding no lesson you must recall. Those countless bent molecules, each one reaching out its invisible handholds toward its neighbors, lie woven together into the single smooth sheet you're looking at, an ocean of tiny linkings resolved into one calm face. The warmth the long day poured into this water still lingers within it, seeping back into the night air so slowly and so evenly that you would never once feel the moment it began to leave. Notice how the far shore appears again upside down upon the surface, its trees and reeds and dark banks hanging into a mirrored sky that seems to open downward beneath your feet without any end. A single leaf floats out from the bank and comes to rest upon the taut skin of the surface, riding there lightly, dimpling the water into a shallow dish beneath its weight without ever breaking through. Where the leaf first touched, faint rings spread outward one after another, widening in perfect circles across the pool until they thin and fade and melt back into the waiting flatness once more. You need do nothing here, only watch and only breathe, and let the deepening evening carry your wandering thoughts out across that dark and level glass to wherever they most wish to travel. Somewhere beneath the mirrored reflection, the water deepens into shadow, cool and untroubled and dark, holding without strain the exact shape of the earthen hollow that cradles it against the sleeping ground. A faint mist begins to gather low over the water, rising up from the surface and softening the reflected stars into blurred and kindly points of pale light that waver gently at the edges. Every wonder that came before now settles into this one restful scene, the way fine sediment sinks slowly downward through still water and comes at last to rest along the soft floor of a shadowed lake. There is no hurry in any of it, and no far edge to reach, only the long, even holding of water at rest beneath the darkening night, going nowhere and needing to be nowhere else. Let the deep hush of this place move slowly into you, so that the stillness of the pool and the stillness gathering within your own chest ease toward each other and become a single thing. Feel how easy it becomes to simply be here beside such water, in a place where nothing pushes and nothing pulls at you, and where time itself seems to gather and pool and slow to a floating halt. Stay here a while longer at the water's edge, in no hurry to leave, letting the mirrored sky above and the sleeping pool below hold you between them, softly and surely, right where you already are. Among all the common liquids found anywhere on earth, water dissolves a wider range of substances than any other, and it is this open-handed appetite that has earned it the old and fitting name of the near universal solvent. Its secret lies in that lopsided shape you met a few chapters ago, one end leaning faintly positive and the other faintly negative, so that every single molecule behaves like a minute magnet reaching for charge. When a crystal of table salt slips beneath the surface, its neat and ordered grid of sodium and chloride is not violently smashed apart, but coaxed loose one ion at a time, working slowly from the outside in. The positive ends of the water molecules turn toward each chloride, while their negative ends swing toward each sodium, and this steady tug of opposite charges draws the crystal apart into a loose scatter of separated particles. Every ion that breaks free is then wrapped in a cradling shell of water molecules, all of them turned inward to face it, holding it gently apart from its old neighbors so it can never snap back into place. Chemists name these embracing wrappers hydration shells, and they are the whole reason a heaped spoonful of salt can vanish so completely into a glass, dissolving away and leaving the water as clear and untroubled as before. Sugars and a great many other compounds dissolve by a kindred trick, offering up their own charged corners for the water to grasp, though these tend to melt into solution as whole intact molecules rather than as split ions. Not everything yields so easily, of course, for oils and fats carry no charge that water can seize upon, so they draw together into droplets and turn away, which is exactly why they float untouched on the top. Picture a mountain stream running clear over stone, loosening a faint trace of mineral from every rock that it crosses, then carrying that dissolved cargo steadily downhill toward the gathering rivers and the wide and waiting sea. Over almost unimaginable stretches of time, countless rivers have delivered their dissolved salts down into the ocean, where the water itself departs again by evaporation, while the salt is left behind to stay and slowly accumulate. That endless gathering is the plain answer to an old and simple question. The reason the sea tastes so strongly of salt while the rain overhead and the rivers feeding it taste of almost nothing at all. Inside living things, this same dissolving power becomes a kind of courier, since blood is very largely water, carrying dissolved sugars, salts, and gases outward to every distant corner of the body that has need of them. Within a tree, the flowing sap performs much the same work, water ferrying dissolved minerals upward from the roots below, and dissolved sugars downward from the sunlit leaves, nourishing every part of the living frame. Because water reaches out so readily to so many things, it almost never travels entirely alone, gathering a little of whatever it happens to touch into an ever-changing broth of dissolved and drifting company. This is the reason perfectly pure water is such a rarity, found only in the careful glassware of laboratories, while the water of springs and rain and household taps always carries a whisper of dissolved minerals and air. Those faint dissolved minerals are part of what lends spring water and old mineral springs their particular taste, the tongue reading delicate traces of calcium and magnesium and salt far too small for any eye ever to see. Notice how utterly ordinary this hidden generosity really is, dissolving forever, happening in your kitchen and your garden and your own living veins without any effort or announcement, all through the day and all through the night. And so the most common liquid you have ever known holds an entire dissolved world within it, cradling and carrying far more than its clear and simple surface could ever seem to reveal. To lift a single molecule of water out of the liquid and set it loose as vapor, every hydrogen bond tethering it to its neighbors must first be pulled completely apart and let go. Breaking all those little handholds at once demands a surprising amount of energy, far more than you might ever expect from something as ordinary as a shallow puddle warming under an afternoon sky. Scientists call this hidden cost the latent heat of vaporization, and for water it is remarkably large, standing among the very highest of any common substance you are ever likely to encounter. Because escaping into the air costs so much, each molecule that finally breaks free must gather that energy from somewhere nearby, and it borrows warmth directly from the water and surfaces left behind. So evaporation is really a kind of stealthy theft of heat, where the fastest molecules escape and carry their energy away, leaving the slower, cooler ones huddled close together below. This is the secret behind sweat, which does almost nothing while it sits on you, and only when it evaporates does it draw heat from your skin as it lifts away into the surrounding air. Notice how a breeze off a lake or river feels cooler than the same wind passing over dry ground, because the moving air hurries the vanishing of water and the removal of warmth with it. A wet cloth laid across the forehead works by this very same principle, cooling not through the water simply resting there, but through the water steadily lifting away and disappearing into the air. Even a simple clay pot filled with water can keep its contents cool through a hot climate, as moisture seeps slowly through the porous walls and evaporates away from the outer surface. Dogs panting in the shade, leaves releasing vapor through tiny pores, a garden misted at dusk, every one of them leans on this single trick of heat carried off by escaping molecules. Consider how little water actually needs to disappear to make a genuine difference to temperature, since so much energy rides away invisibly on each departing wisp of vapor that rises from a surface. A thin film of moisture, barely enough to darken the face of a stone, can pull away sufficient warmth to leave that stone noticeably cooler than the air standing all around it. On the scale of the whole planet, this same modest effect becomes something vast, an enormous and unhurried air conditioner spread across every ocean, every forest, and every rain-soaked field of the world. Sunlight pours down into the tropical seas, and instead of simply roasting the surface into a blaze, much of that energy is spent lifting water up into the sky as invisible vapor. That stored heat travels along with the rising air, journeying for hundreds of miles before it is finally released again, high overhead at the moment the vapor gathers itself back into cloud. In this way, water spreads warmth outward from the blazing equator toward the far cooler poles, smoothing the planet's temperament much more evenly than bare rock or dry sand could ever manage alone. Hold that picture in mind for a while. The whole world kept temperate by nothing more dramatic than water turning to vapor and carrying its stored heat along the sky as it drifts. A little water vanishing without ceremony from skin and leaf and open sea carries off a great weight of warmth, and in doing so it keeps the whole living world beautifully cool. Just as evaporation carries warmth away into the air, freezing works in the opposite direction, releasing the very heat that liquid water had been holding within its restless web of hydrogen bonds and returning it to the world outside. When liquid water crystallizes into ice, each molecule eases into its fixed place and lets go of a small parcel of stored energy, a quantity of warmth that spills outward into the surrounding water, the air, and whatever else lies nearby. Notice the strange balance hidden in this exchange, for as ice melts it drinks in a great deal of heat without its temperature climbing even a single degree, staying fixed at freezing for as long as any solid remains. That hidden warmth carries a name physicists gave it long ago, the latent heat of fusion, where latent simply means concealed, the heat tucked inside a change of form rather than revealed as any change of temperature. Picture a pitcher of ice cooling a summer drink, and notice how it holds the liquid near freezing for a surprisingly long while, because every melting sliver must first absorb energy before the water is free to warm at all. The ice is not merely cold, you see, but genuinely thirsty for heat, and it keeps drawing warmth from the surrounding liquid, sip after sip, until the very last crystal has softened and disappeared into the drink. Only once every last fragment of ice has finished melting does the temperature of the water begin, at long last, to climb again, rising slowly toward the ordinary warmth of the room that surrounds it. Freezing performs this same trade in reverse, so when frost gathers across a window pane overnight, each forming crystal gives back its hidden store of heat, breathing that warmth outward into the cold night air pressing against the glass. On a still autumn evening, orchard growers sometimes spray their trees with a fine mist of water, precisely because the freezing of that water releases enough warmth to shield the tender blossoms from a killing chill. A pond surrendering to the coming of winter behaves like an enormous reservoir of concealed heat, giving off its warmth for hour upon hour as its surface slowly hardens and thickens into a solid sheet of ice. Consider how much energy this hiding truly involves, for melting a given mass of ice demands very nearly the same amount of heat as it would take to warm that identical water by a full 80 degrees Celsius. Because of this vast appetite for warmth, ice and snow act as a kind of thermal ballast, steadying the temperature of an entire landscape through the long and changeable turning of the year from season to season. Spring itself arrives more slowly wherever great fields of snow still linger on the ground, since every drift must swallow an enormous quantity of warmth, degree by degree, before it can finally soften and melt away. Autumn, in much the same manner, is gentled by all the freezing still to come, as each forming sheet of ice pours its stored heat back into the surroundings and softens the long descent toward the deep cold of winter. Across whole continents, this yearly rhythm of water melting and freezing blunts the sharp edges of the seasons, trading the fierce extremes of heat and cold for something gentler, steadier, and far more even in its passage. Consider that quiet accounting for a moment, warmth taken in without any rise in temperature, warmth given back without any drop, a whole ledger of energy balanced entirely within a single change from one state to another. There is a deep economy at work here. The way water tucks its energy away out of sight as it freezes, and then returns that same warmth later as it melts, never once announcing the heat it carries. Water hides its heat away as it freezes, and reveals that heat again as it melts, and through this endless, unseen exchange it holds the whole living world a little steadier than it would otherwise ever be. 0 degrees Celsius is the temperature where we expect ice to appear, and yet under just the right conditions, water can slip past that familiar mark and remain fully liquid, as though it had somehow forgotten the rule it is meant to obey. This lingering liquid state, chilled well below its ordinary freezing point while stubbornly refusing to harden into a solid, carries a rather lovely name that scientists long ago gave it, a word worth saying, softly supercooling. To become ice, a volume of water needs far more than cold alone, because the orderly crystals of a solid cannot simply wish themselves into being out of the restless jostle of the liquid. What they require instead is a starting place, a tiny seed of order, some small anchor around which the wandering molecules can begin to align themselves into the first delicate beginnings of a lattice. In everyday water, that seed arrives without any trouble, offered up by a floating fleck of dust, a faint scratch along the glass, or a stray bubble clinging to the wall of the container. But remove those small imperfections, keep the water pure and perfectly undisturbed, and the molecules find nowhere obvious to begin, so they go on hovering in liquid form far below the temperature at which you would expect them to freeze. In careful conditions, you can chill such water many degrees beneath zero, in the purest cases approaching 40 below, and still it will sit there clear and untroubled, holding its breath at the very threshold of ice. Then comes the moment that feels almost like a small conjuring trick, a flash of something magical, though in truth every part of it obeys the plainest and most ordinary rules of physics. A single tap against the side of the bottle, one sudden jolt, or one tiny introduced speck of dust is enough to give the waiting molecules the anchor they had been missing all along. From that first single point, order races outward through the entire vessel in a heartbeat, and the freezing that would ordinarily unfold across long, slow minutes instead finishes in a matter of mere seconds. You can picture a feathery wave of white ice suddenly blooming outward from the very spot you touched, spreading like the frost that writes itself across a cold window pane, only quick enough to watch it travel. Each newly frozen molecule becomes a fresh foothold for the next one to latch onto, so the transformation feeds upon itself and sweeps through the whole of the liquid in one unbroken continuous surge. Notice how the water had seemed so utterly ordinary only an instant before, and how astonishingly little it took to release the great change that had been waiting silently inside it the entire time. Far above your head, this very same hesitation plays out on an immense and sprawling scale, hidden away within the pale drifting sheets of high cloud that stretch across the winter sky. Countless tiny droplets up there are themselves supercooled, floating well below freezing and yet stubbornly still liquid, simply because each one is far too small and too clean to ever find a seed of its own. They go on lingering in that suspended and uncertain condition until a passing ice crystal or a wandering mote of dust happens to brush against them and finally invites each droplet to freeze at last. Much of the rain that eventually reaches the ground begins its life as exactly these reluctant droplets, water balanced on the very edge of ice, waiting for some small trigger to tip it over. Carry that image gently with you as you rest. Then, water held poised between two states, steady and unhurried in the cold, needing only the lightest touch to find its final shape at last. Among the many understated talents of water, one of the strangest is its stubborn refusal to shrink, holding its exact volume no matter how firmly the world leans in and presses against it from every side. Squeeze a gas and it folds inward willingly, its scattered molecules crowding closer together into a smaller space. Yet liquid water holds its ground, its volume barely yielding even under enormous and unrelenting force. You could press down on a sealed flask of water with the whole weight of a small car resting upon it, and even then its size would change by only the very faintest sliver. This near-total refusal to be compressed arises from how closely the molecules already sit against one another, linked by their hydrogen bonds into a dense crowd, with almost no empty room left anywhere to give. Picture the deep ocean kilometers down in the dark, where the immense weight of water overhead presses with a force that would crumple most hollow things into flattened scraps of twisted metal. Even down there, under that crushing pressure, the sea does not collapse into some thin, heavy sludge slumped uselessly along the seafloor, its water remaining as fluid and mobile as it ever was above. Instead, the water grows only slightly denser, compressed by just a small few percent even at the greatest depths, and remains open, vast and brimming with room for currents and living creatures to move. Because of this, an ocean 2 or 3 kilometers deep is not thin watery soup at the bottom and airy froth at the top, but one great continuous body, much the same from surface to floor. Consider how remarkable that steadiness truly is, that a substance so soft and yielding to the touch of your hand becomes, under real pressure, one of the most unmovable things you will ever lean your weight upon. Engineers learned long ago to trust this trait, letting water and other liquids carry force faithfully and without loss from one place to another through slender sealed pipes and narrow channels. Press on the fluid at one end of a hydraulic line, and because it simply will not compress away into itself, that push travels onward almost whole to lift great weights at the far other end. The brakes that ease a car to rest, the arms that raise a heavily loaded platform, the presses that shape sheets of steel, all lean upon this refusal of liquid to be shrunk aside and wasted. Turn now from great machines to something far smaller and alive, to a single microscopic cell resting somewhere within the flesh of a leaf, a blade of grass, or the tip of your own finger. Each tiny cell is filled with a watery fluid that presses steadily outward against its thin surrounding wall or membrane, and that gentle inner push helps hold the whole cell in its firm, rounded shape. Because the water within simply cannot be compressed, it behaves almost like a cushion of held breath, bracing the cell from the inside and keeping it plump and full rather than caving weakly inward. Wilting, that drooping a plant suffers in the dry heat of afternoon, is partly this inner water pressure fading away, the countless little cells losing the firmness that once held every stem and leaf upright. So the very same trait that makes the deep sea so vast and steadies the arm of a hydraulic press also lends a hidden structure to the soft living things that carry water within them. And as the hour grows late, you might picture water everywhere, pressing calmly back against all that presses upon it, unshrinking and undefeated, holding its own fullness through every force the world can bring. Listen for a while to the rain arriving on the roof above you, a sound so woven into your life that you may never once have wondered what it is truly made of, or why it seems to loosen something tight inside the mind. What you hear as one long, continuous hush is really countless separate arrivals, each single raindrop its own tiny impact, thousands of them striking every second across the tiles and the gutters and the broad, flat leaves of the trees. No single drop is loud on its own, and no two ever land at quite the same instant, so their small individual taps overlap and blur together into one seamless, unbroken wash of sound with no seam left to hear. Because that wash of sound has no sharp beginning and no urgent end, your listening mind can find nothing within it to fasten onto, nothing that rises up to demand being watched, decoded, or answered. A sudden noise yanks your attention sharply outward toward its source, but the rain does exactly the opposite, offering instead a wide and even field of sound, broad enough for your thoughts to loosen their grip and wander. Somewhere out beyond the window a small stream is moving over its bed of stones, and its voice is built the very same way from thousands of little collisions of water against rock and against its own tumbling self. Each ripple that folds and curls over a pebble traps a small bead of air beneath it, and when that captured bubble finally bursts, it releases one faint musical note, one of the many that braid together into the brook's low murmur. Notice how these water sounds carry no words in them and no warning of any kind, only a texture, a gentle and shapeless randomness that the ear can lean against the way your tired body leans into the waiting bed. From the eaves, a slow occasional drip keeps its own unhurried time, one drop, then a long pause, then another drop later, marking out a loose rhythm far too irregular to count yet somehow easy to follow. There's a particular comfort in a rhythm that never insists on itself, one that arrives whenever it happens to arrive, asking nothing of you whatsoever, beyond that you notice its passing and then let it go. Under the dripping eaves and out along the darkened branches, the whole wide roof of the world seems to be speaking softly to itself in this low and even language made entirely of falling water. Scientists who carefully study such sounds describe them with the word broadband meaning a wide and well-balanced spread of many tones all mixed together, with no single sharp pitch reaching out from the blend to seize and hold your attention. That deep evenness is a close cousin to the steady hush that engineers deliberately create to mask other, harsher noises, a sound engineered to fill the empty edges of a room and smooth every sharp corner out of the air. So when the rain gradually steadies you down toward sleep, it is not lulling you with any hidden secret or trick of its own, only offering a sound too mild and too endlessly varied for your mind to keep itself sharp and alert against. Let the layered patter float down over your thoughts, the way a light spring rain falls upon an open field, touching everything at once in the same moment, and yet pressing down hard on nothing. Each single drop has fallen an enormously long way through the dark to reach this one roof, from distant cloud to open sky to here beside you, and its small tap is the final, unremarkable end of that long descent. You need not chase or follow any single one of all these sounds. Only let them gather loosely around you on every side, a wide and living stillness that has no center to find and no edge anywhere to hold. Breathe slowly along with the rain, then, and let its endless, soft arriving carry your listening down and down, deeper yet, until the sound outside and the rest within you have become very nearly one and the same thing. The ice cube clinking in a glass, the delicate frost etched across a cold window, the snow settling in soft drifts over a rooftop, all belong to a single familiar form of frozen water, and that form is only one of a surprising many. Here on the mild surface of our world, water almost always freezes into the same open, six-sided arrangement, a shape so ordinary and so expected that we simply call it ice and never think to look any further. Yet chemists probing the extremes of cold and pressure have counted more than a dozen distinct crystalline forms that water can take, each one a wholly different way of stacking the very same small bent molecules together. What decides between all these forms is not some hidden essence or secret ingredient, but two plain physical conditions: the temperature of the water and the pressure bearing in upon it from every side at once. Squeeze water hard enough, or chill it in unusual and carefully controlled ways, and its molecules abandon their roomy everyday lattice for tighter, more crowded geometries you would never once encounter in an ordinary kitchen. Scientists label these hidden forms with numbers: Ice 2, Ice 3, Ice 6, and onward through the list, a modest and growing catalog of the many separate architectures a single simple substance can secretly assume. Picture the same identical building blocks rearranged, like a child's blocks tipped out and stacked from one pattern into another, the molecules themselves entirely unchanged, only the rooms and spaces between them drawn anew. In several of these crowded high-pressure forms, the molecules pack so closely and so efficiently that the ice becomes denser than the very liquid it came from, a startling and complete reversal of the floating ice we know. Such heavy ice would never bob at the top of a glass the way a cube does. It would sink instead, settling slowly downward rather than rising the way our familiar frost always prefers to do. You are unlikely ever to hold one of these exotic forms in your hand, for most of them demand pressures many thousands of times greater than the gentle weight of air resting on your shoulders tonight. Deep inside the icy moons of the outer planets, far beneath their thick crusts of frozen sea, such compressed and heavier ices are thought to exist in enormous hidden layers pressing down toward the rocky cores. Within the vast, heavy bellies of giant worlds like Neptune and Uranus, water may be crushed into exotic and unfamiliar forms far removed from anything a bright winter morning here on Earth could ever show you. Consider how strange it is that the very substance filling your glass takes, out in the wider cosmos, exotic and crowded shapes that no human eye has ever once directly seen, hidden away in places we cannot reach. Our buoyant, floating ice, the very kind that caps our winter lakes and shelters the slow fish waiting below, turns out to be the roomy exception among water's many forms rather than the universal rule. It floats only because its ordinary lattice is unusually spacious, holding each molecule at arm's length from its four neighbors in an airy open cage that most of water's other denser forms simply do not keep. Change the pressure enough and that generous openness collapses inward, the molecules drawing nearer to one another, the ice growing steadily heavier, and the whole familiar floating behavior turning entirely inside out as if some rule had been rewritten. Let yourself marvel that one plain compound, learned in childhood as a single tidy formula of 2 hydrogens and 1 oxygen, can wear so many different crystalline faces depending on where in the wide universe it happens to rest. The frozen water of Earth is merely the one dialect we happen to speak from birth, while the cosmos, in its cold and pressure-crushed depths, knows a full dozen others by heart and speaks them freely. Beneath the smooth face of an icicle or a frozen pond lies an order so exact that it repeats the very same 6-sided pattern countless times over, molecule after molecule, stretching on without a single wandering or misplaced step. When liquid water finally cools past its freezing point, the restless molecules give up their tumbling and settle into fixed positions, and each one reaches out to hold exactly 4 neighbors arranged toward the corners of an imagined little pyramid. Picture one molecule sitting at the center, tethered by hydrogen bonds to 4 others spaced evenly around it, forming the small tetrahedral handshake that becomes the seed and template of everything the whole growing crystal will eventually be. Because 4 is the favored number of bonds each molecule insists upon, those tetrahedral links cannot fold up tightly upon themselves, and instead they fan outward into open rings of 6, the hexagon written again and again throughout the ice. 6 of these molecules join hands into a single puckered ring, and ring stacks upon ring layer by layer, so the crystal grows in the same 6-fold symmetry you can trace faintly in the arms of any snow crystal. Notice how a hexagon, unlike a solid packed block, must enclose a hollow middle, and it is precisely this built-in hollowness that hands ordinary ice its most surprising and generous secret of all. Where the molecules in liquid water jostle close and pack in wherever they happen to fit, the forming crystal instead insists that everyone stand a fixed arm's length apart in that open, ordered cage of hexagons. Threaded straight through the whole lattice run wide, empty channels, tiny tunnels of pure nothing, spaces propped open by the geometry itself, rather than filled in by any wandering molecule looking for somewhere to settle. Those hollow channels are the reason a cube of ice weighs less, gram for gram, than the very puddle it froze from, since the same number of molecules now occupy noticeably more room than they did before. Freezing for water is therefore a rarer act of expansion, the substance spreading itself into a roomier architecture, and that hard-won extra space is exactly what lets a sheet of ice ride buoyant upon its own liquid. Almost every other substance on Earth grows denser and heavier as it hardens, sinking down beneath its own melt, yet water alone builds a scaffold too airy to sink, and so its ice climbs up to the surface instead. Think of the whole lattice as a honeycomb turned three-dimensional, a small cathedral of slender struts and vaulted gaps where structural strength and sheer emptiness are woven together into one endlessly repeating design. Each hexagonal ring is a kind of fingerprint of the hydrogen bond, a faithful record of that four-armed reaching, printed over and over at a scale far too small for your unaided eye to ever resolve directly. You could shrink yourself down and wander the corridors of this crystal almost endlessly, meeting the same six-sided rooms in every direction you turned, the pattern holding faithful across billions upon billions of identical molecules. Warm the ice even a little, and those bonds loosen their grip. The open cage collapses gently inward on itself, and the molecules tumble back down into the closer, denser, more crowded jostle we simply call water. So the whole difference between floating and sinking, between a lake sealed under a thin lid or frozen solid clear down to its bed, comes down to this single choice of geometry made at the freezing point. Let yourself marvel a while at the strangeness that emptiness itself can be a kind of structure, that a substance can grow lighter precisely by becoming more orderly, more spacious, and more certain of its own open shape. Every hexagon and every crystal of ordinary ice, from the frost feathering a window pane to the deep blue heart of a glacier, carries this same simple arithmetic of four bonds, six-sided rings, and the wide open room held between them. Everywhere else in this episode, the freezing of water has meant order, its molecules gliding into the tidy six-sided lattice that lends a snowflake its symmetry. Yet there is another stranger path that a cooling droplet can sometimes take instead. Cool a droplet of water swiftly enough, far faster than its molecules can ever find their proper places, and they seize up exactly where they stand, locked into a frozen jumble that never resolves itself into a crystal. This curious form is called amorphous ice, a true solid that nonetheless keeps the tangled, disordered arrangement of a liquid, holding no repeating pattern and no orderly lattice anywhere within its structure. Picture a great crowd suddenly told to freeze mid-step, their arms and glances caught at every unrepeated angle, held just as they happen to be standing, and you have a fair sense of how these molecules are arranged. Because the chill arrives before the tiny hydrogen handholds between molecules have any chance to rearrange into order, no true lattice forms, and the water hardens instead into something far closer to a kind of glass. Glass, after all, is simply a solid that has kept the messy, wandering inner structure of a liquid frozen into place, which is precisely what happens to a droplet of water chilled this abruptly. You might well expect such an oddity to be rare, little more than a laboratory curiosity coaxed into being only under carefully controlled and quite unusual conditions here on the surface of the earth. Yet here comes the true marvel of this chapter, a fact that reaches far, far beyond any frost you have ever traced with a fingertip on a cold window pane in the depths of winter. Amorphous ice is, by an enormous and almost unimaginable margin, the single most common form of water anywhere in the entire universe, utterly dwarfing every snow crystal and every rolling ocean we have ever known. Out among the stars, within the vast and frigid clouds of gas, where new suns are slowly gathering themselves together, water freezes onto tiny specks of floating dust, arriving and sticking one lone molecule at a time. Space is so profoundly cold, and the molecules travel in so sparingly across the emptiness, that they simply stick fast wherever they happen to land and never gain the warmth they would need to settle into ordered ranks. Each single grain of interstellar dust wears a thin coat of this glassy ice, an unseen frost invisibly clothing untold trillions upon trillions of particles scattered through the immense darkness that lies between the worlds. Comets carry it too, their dark and ancient surfaces sheathed in this same formless frost, preserving the glassy ice almost entirely unchanged across looping journeys that can last many thousands upon thousands of years. Consider, as you lie there at ease, that there is far more of this disordered, glassy water floating silently among the stars than all the liquid water gathered in every sea and river our own world holds. The very same substance now filling your glass and running through your rivers exists mostly out there in the deep dark as a shapeless frozen film clinging to countless grains no wider than a wisp of smoke. It has been forming in just this way since long before the earth itself existed, laid down grain by slow grain within the very clouds that would one day collapse inward to become new stars and planets. So the familiar flowing liquid you have always known is, cosmically speaking, the rare exception rather than the rule, while this silent glassy ice is the true and ordinary face that water wears across creation. So carry this quiet wonder into the night as you rest, that nearly all the water in all of creation waits out there in perfect stillness, formless and frozen, glinting faintly in the spaces between the stars. Among all the countless substances scattered across the earth, water is one of the very few you routinely meet wearing three entirely different faces, sometimes all of them within the ordinary span of a single unremarkable day. There is the solid you crack from an ice tray in the freezer, the flowing liquid you pour into a waiting glass, and the invisible vapor that rises unseen from a warm cup toward the ceiling above. Most other materials keep faithfully to a single form at the temperatures we live among, staying stubbornly rock or unbending metal or thin air, never once troubling to change their state while we happen to watch. Water, by contrast, moves freely between its three states at temperatures your own bare hand can easily reach, and that ready shifting is part of why it feels so ordinary, so familiar, and so oddly companionable. Picture a cold winter morning where frost feathers across the window, a thin stream trickles somewhere below, and mist curls off the open water into the freezing air, all three forms gathered into one small scene. Each of these three faces is built from the very same little molecule, merely holding its neighbors more tightly or more loosely, arranging and rearranging itself as warmth flows steadily in or slowly ebbs away again. In ice, the molecules lock into a fixed and rigid lattice. In liquid, they tumble and slide past one another freely, and in vapor they fly wholly apart to wander alone through the surrounding open air. Now imagine coaxing a small sample toward one truly extraordinary crossroads, a place where temperature and pressure are both tuned at once to a single exact and delicate combination that scientists have named the triple point. At that one precise meeting place, something genuinely remarkable becomes possible, for solid and liquid and vapor can all exist together in the very same moment, none of them winning out and none of them fading. Ice and water and floating vapor hold there as perfect equals, coexisting in a balance so remarkably even that individual molecules cross freely between all three forms without any single one of them ever prevailing over the rest. For ordinary water, this delicate crossroad sits at a temperature just barely above freezing, close to 1/100th of a degree, and at a pressure far thinner than the everyday air pressing around you now at sea level. Nudge those conditions even a little, a touch warmer or cooler, a shade heavier or lighter in pressure, and the fragile three-way truce dissolves almost at once as one form begins, without fuss, to overtake the others. What makes this single point so treasured by scientists is not its rarity alone, but its astonishing steadiness, for it returns faithfully to the very same temperature and pressure every single time it is carefully reached. Because that fine balance proved so reliable and so endlessly repeatable, it was once chosen to help anchor the temperature scale itself, standing as a fixed and trustworthy rung against which delicate thermometers could be measured and set. Rather than depending on any single thermometer that might slowly wander or slip over time, careful measurers turned instead to water itself, letting its triple point mark one dependable landmark on the long ladder of warmth and cold. There is something reassuring in that idea that a shivering, trembling balance of ice and water and faint mist could serve as one of the cornerstones for the way human beings measure and mark out the world. Consider for a moment how the same familiar stuff that frosts your window at dawn and fills your singing kettle at night also sits in cool laboratories, helping to define what a single degree of temperature truly means. Carry this last image gently down with you as you rest. The triple nature of water forever poised between three ways of being, each of them resting only a single breath of warmth apart from the next. Set a glass of water on the table beside you. Watch its surface settle into a perfect, unbroken stillness, and let yourself believe just for a moment that nothing is moving anywhere inside it. Look closer than any eye could ever reach, down past the surface shimmer to where the molecules themselves live, and you would come upon a scene utterly unlike the calm and settled world above. Each tiny molecule is forever reaching out toward its neighbors, clasping them through the fleeting hydrogen bonds we met in an earlier hour, and holding on for the briefest imaginable instant before letting go again. A single one of those bonds lasts only about a trillionth of a second, a span so impossibly brief that it forms and breaks again faster than any word or passing thought could ever follow. Multiply that vanishing instant by the countless molecules crowded into a single mouthful, and the bonds within are breaking and reforming trillions upon trillions of times over in the space of one ordinary second. Picture a vast candle-lit ballroom where every dancer clasps a partner, releases without pause, and reaches at once for another, all of them swapping hands endlessly in a blur far too swift for any eye to see. No molecule keeps its companions for long, each one flickering between connection and release, joining, parting, and joining again and again in a ceaseless rhythm that never once pauses to draw breath. What your eye reads as a smooth and unmoving pool is in truth a shimmering restlessness, an unending exchange humming away far beneath the threshold of anything you could ever notice or measure. Order and disorder trade places here without end, the bonds knitting the molecules into fleeting little clusters that dissolve almost the very instant they appear, only to gather themselves and form all over again. This restless flux is the very reason liquid water flows so freely, rather than holding a rigid shape, for its bonds are far too brief and too fleeting to lock the molecules into any lasting arrangement. Warm the water, and the dance grows wilder still, the bonds snapping and rejoining ever more furiously as the molecules borrow energy from the heat and move faster and faster among one another. Cool it back toward freezing, and the tempo gradually eases, the exchanges slowing and slowing until, at the last, the molecules settle into the ordered lattice of ice, and the swapping very nearly stops. Yet even in the settled glass at your bedside, resting at the ordinary warmth of the room, That inner motion carries on with a vigor no amount of outward stillness could ever truly betray to you. Nothing about this endless churning is chaotic in any troubling sense, for it obeys the deep and dependable rules of physics, a restlessness woven straight into the fundamental nature of water itself. Consider how strange it is that the very substance we reach toward when we long to feel calm should be, in its smallest and most hidden workings, one of the busiest and most animated things imaginable. Every sip of water you have ever taken was alive with this flickering, its molecules trading partners billions upon billions of times over before the liquid even touched your lips or crossed your waiting tongue. So let the paradox soothe you rather than stir you awake, this hidden dance that asks nothing whatever of you and simply continues indifferent and tireless whether you choose to watch over it or not. Beneath the mirror-flat surface glimmering faintly by your bedside, an untold multitude of tiny hands goes on reaching, clasping, and releasing, a silent, endless motion that has never once grown weary and never will. Imagine a glass of water so pure that nothing has been added to it, no salt, no mineral, no trace of anything else, only molecules of hydrogen and oxygen resting together in the dim, unlit air of the evening. Even here, within this perfect clarity, something faint and genuinely remarkable is forever underway, a whisper of ceaseless change that never once pauses to rest and never announces itself to the eye that watches the still surface. Every so often, two neighboring molecules float close enough to touch, and one of them passes a single hydrogen across to the other, so the pair splits apart in the smallest exchange that chemistry allows anywhere in nature. Where a moment before there had been two ordinary balanced molecules, there are suddenly two opposite ions instead, the one carrying a little extra positive charge and the other left holding a matching touch of negative. Chemists have given this self-splitting a name of its own, autoionization, an unhurried word for the way water breaks a small fraction of itself apart without any push or help arriving from the world outside. You might well expect such a thing to be rare, and rare it truly is, rarer by far than almost anything else you could picture unfolding inside the plain and unremarkable glass at your bedside. At any single instant, only about one molecule in several 100 million has actually come apart into ions, while all the countless hundreds of millions of others around it remain whole, intact, and entirely unchanged. Picture a vast crowd stretching farther than any eye could follow, and understand that among that entire uncountable multitude only a scattered handful here and there have traded away a small fragment of themselves. These split pairs never last for long, and almost as soon as they form they find one another once again and rejoin into whole molecules, even as new pairs are born elsewhere in the water to take their place. So the very faintest breath of charge runs endlessly throughout the whole volume of the water, forever appearing and vanishing again, a spark far too small to feel on the skin yet present within every part of it. From this delicate, endless self-splitting comes something whose name you may well have heard spoken before, the idea of pH, the familiar measure by which we weigh how acidic or how basic a liquid happens to be. An acid, in its simplest description, is a substance that adds still more of those positive hydrogen fragments into the mix, tipping the delicate balance a definite step away from where lone water would otherwise sit. A base does exactly the opposite, either drawing those positive fragments away or offering their negative counterparts in their stead, and so it tilts the same scale by a measured degree toward the far side. Pure water, left entirely to its own devices, holds these two opposing kinds in precisely equal number, the very same tiny count of positive and of negative ions wandering forever through its clear and silent depths. Because that balance is so perfectly matched, we say that pure water rests at the neutral middle of the scale, at the value we call a pH of 7, belonging to neither side and favoring nothing. There is a certain steady poise in that, a substance so remarkably even-handed that it has become the very center of the whole scale, the fixed origin from which every acid and every base on earth is measured. Let yourself picture it all once more, that clear and settled stillness humming faintly with its almost invisible activity, splitting and mending and splitting again far beyond the reach of any eye that might try to see it. Within even the plainest water, then, there lives this faint inner spark, ceaseless and perfectly equal, the silent origin of a balance that reaches into every river, every cloud, and every last drop on earth. Not every drop of water is built from exactly the same parts, for hidden among the countless ordinary molecules is a rare and heavier cousin, one that has drifted through our rivers and seas since long before anyone ever thought to look for it. To picture the difference clearly, imagine first an ordinary hydrogen atom, the lightest atom there is, which carries just a single tiny particle, a lone proton, at its very center and nothing whatsoever beside it. Now and then, however, nature assembles a hydrogen with one extra particle tucked snugly alongside that proton, a neutron, and this slightly weightier version of the atom has long since earned a name of its own, deuterium. When two of these heavier hydrogens come together with a single oxygen atom, in place of the usual lightweight pair, they form the curious liquid that chemists have long and simply called heavy water. Look at a glass of it under the lamp, and you would notice nothing at all unusual, for heavy water is every bit as clear, as wet, and as ready to pour as the water you know. Its taste is very nearly indistinguishable. Its freezing and its boiling arrive at almost exactly the same familiar marks, and to any casual glance the two liquids seem like perfect and untellable twins. Beneath that easy likeness, though, hides one honest and measurable difference, because the extra neutron carried within every hydrogen makes each single molecule of heavy water noticeably weightier than its everyday counterpart. Add up all those small surpluses across an entire glassful, and heavy water tips the scales roughly a tenth heavier than the plain water you likely drank this very morning without a thought. That added heft is enough to overturn one of water's most famous and beloved habits, the effortless way in which ordinary ice rides buoyant and bright upon the surface of a winter pond. Freeze a little heavy water into a solid cube and lower it into an ordinary glass, and instead of bobbing contentedly at the top, it will settle slowly and steadily toward the very bottom. Such a sinking cube of ice can look almost like a small conjuring trick, and yet it follows plainly and inevitably from the simple fact that the heavier ice outweighs the lighter liquid surrounding it. Despite this curious and slightly startling behavior, heavy water is astonishingly scarce in the world, present only as the faintest whisper woven all through the ordinary water that fills every river and sea on earth. Scoop a whole heavy bucket straight from the sea, and the rare heavier molecules hidden within it would amount to little more than a few scattered drops lost among trillions upon trillions of the ordinary kind. Because it hides in such a faint and thinly spread proportion, no one can ever simply pour out a ready bottle of it, and gathering any real quantity demands long, careful, and painstaking separation. Refineries coax the heavier twins slowly forth by processing enormous volumes of ordinary water over and over again, letting the weightier molecules grow just a little more concentrated with each unhurried and repeated pass. For all the effort and slow care such gathering demands, this rare twin more than earns its keep, serving deep within certain nuclear reactors where its unusual heaviness helps to slow and steady the restless motion of neutrons. Researchers prize the heavier molecules too as a silent and faithful marker, following their added weight through living tissue or across whole oceans to trace slow journeys that would stay invisible to any other tool. So as sleep gathers softly around you now, hold on to this one small marvel, that even the plainest water keeps a heavier, secret self, waiting rare and unseen within everything so familiar and near. Fill a glass at the tap tonight, hold it toward the lamp, and watch how the light slips clean through it, as though the water were scarcely there, offering almost no resistance to the glow, and throwing only the faintest shadow onto the table. That transparency is one of the deepest gifts water has given to life, for a substance clear enough to see through is also a substance through which an eye can one day be built to look, a window opening both ways at once. Somewhere far back along the long branching story of living things, vision itself could arise precisely because seawater lets sunlight travel down into it, carrying faint pictures of the surrounding world to whatever creatures first learned how to read them. Imagine, just for a moment, how differently that whole story might have gone if the early seas had been murky as tar, closing every window against the sun and dimming the depths before a single lens or eye could ever form. Clarity, then, is far from nothing. It is a kind of standing permission, a plain transparency that opened the way for living creatures to trade in light and shadow and shape, learning the shape of the world through watching eyes. And yet, for all its openness and all its glassy clearness, water is not truly colorless after all, and this is the small secret it keeps folded away inside every ocean, every river, and every deep mountain lake. Genuine, faint, and entirely real, water carries a color of its very own, a blue so pale and so understated that a single glassful held up to the light can never once reveal it to your searching eyes. The reason lies in the way each molecule answers the light that enters it, absorbing just a thin whisper from the red end of the spectrum as those particular waves travel onward and deeper through the gathered depths of the water. Red light, the warm and long wavelength end of the rainbow, is nibbled away first of all, taken up bit by bit, and surrendered to the water as it presses steadily downward below the bright and shining surface. Blue light, being shorter and cooler in its wavelength, slips onward almost entirely untouched, so that the deeper down you happen to look, the more the light returning to your eye leans toward that clear and even hue. In a single ordinary glass, the effect stays far too slight for anyone to notice, since the light has almost no distance to cross before it passes straight back out again to reach your waiting eye. Gather a great volume of water together, though meters upon meters of it stacked into depth, and the missing red at last begins to tell, leaving behind a blue that deepens and grows richer with every added fathom. This is the true reason a clear mountain lake can hold such a startling, luminous blue even on a gray day when no cloud and no patch of open sky lean over it to lend a single reflection. People long assumed that lakes and seas merely borrowed their color from overhead, acting as a wide mirror tilted upward to catch and echo back whatever shade the heavens happened to be wearing in that hour. Reflection does play a genuine part, scattering the image of the sky across a ruffled and wind-touched surface, and yet beneath that restless shimmer lies a truer blue, one that belongs to the deep water itself. Divers come to know this feeling well, descending slowly until the warm colors fade from sight one by one, the reds vanishing first, then the oranges and the yellows, until the whole surrounding world has settled into a deepening indigo. Picture that slow dimming of the reds as you sink downward in thought, each warm shade released and left behind above you, the water holding on to only the cool, faithful blue it had carried within it all along. Let that pale blue rest easy in your mind now, not a passing trick of the sky, nor any stain hidden in the glass, but the honest, inborn color of water gathered deep and seen at last for what it is. Every living thing we have ever discovered, from the tallest redwood swaying on a ridge to the smallest bacterium afloat in a warm and shallow sea, is built around water, woven through with it from the very first moment of its existence. Your own body is close to 2/3 water by weight, so that in a real sense you are less a solid standing thing than a warm and salted ocean that has somehow been given a shape and held gently together. Within you lie many trillions of tiny cells, and each one is a small enclosed pool, a single droplet of salty fluid wrapped in a delicate membrane, keeping its own private sea apart from all the others pressed around it. Life did not merely happen to begin in water and then climb ashore and leave it behind, for in truth it never left, carrying the ancient ocean inward and sealing a small portion of it inside every living wall. Think of water less as something a creature simply needs, and more as the very stage upon which all the intricate chemistry of living plays itself out, one reaction after another, through every moment of a lifetime without pause. Nearly every reaction that keeps a creature alive unfolds among molecules dissolved in water, moving together and parting again within that crowded liquid, for almost nothing useful in biology can happen while the ingredients stay locked and dry. Because water loosens so many substances apart and then carries them along its currents, it becomes the great courier of the body, ferrying sugars, dissolved salts, oxygen, and chemical messages from one waiting place to the next. The long, elaborately folded molecules of life take their proper working shapes only while surrounded by water, which nudges and cradles them from every side until each one settles into the exact form its particular task demands. A protein tucks its oily, water-fearing parts inward, away from the surrounding liquid, and turns its water-loving parts outward toward it, and from that simple opposing push and pull, an intricate molecular machine folds itself into being. Notice how the same liquid that sculpts those molecules also cushions them, filling every space between, softening each collision and jostle so that the fragile inner architecture of a living cell is never left roughly exposed. Water threads through the crowded interior of every cell like a universal connecting medium, touching almost everything at once and linking one chemical process to the next, so the whole intricate machinery works as a single, continuous conversation. Heat that might otherwise spike and plunge with each passing hour is soaked up and absorbed by all the water held within you, keeping your inner weather remarkably steady even as the world outside warms and cools. In a genuine and almost literal sense, then, a living body is simply water that has been carefully organized, folded into elaborate structures, and set to work at the endless, unglamorous business of staying alive. Consider that the small, warm sea you carry within you is close kin to the ancient ocean, where life first stirred into being, its faint inner saltiness a lingering echo of that distant early shore. Should the water ever drain away, the chemistry falls silent, the carefully folded shapes slump and unravel, and the whole living conversation stills at once, which is exactly why every creature guards its inner moisture so fiercely. Even a bone-dry seed or a dormant spore is not truly dead, but only waiting, holding its intricate structure in trust through drought and dark until water returns to wake its sleeping chemistry back into motion. There is something strange and lovely in the plain fact that the very substance filling the world's rivers and floating clouds is the same one now moving through the mind that turns these thoughts over in the dark. So the cradle was never a place set apart from the child it held, for the same water that once rocked the first faint spark of life became, across unimaginable stretches of time, the living creature itself. Consider, as the evening deepens around you, that the water resting in your glass has been traveling one enormous circle for billions of years, never arriving anywhere final, never once beginning again from nothing. Warmth from the sun coaxes it upward from the sea, lifting it molecule by molecule into vapor that climbs through the wide and waiting air, each tiny departure carrying away a little heat as it goes. High above, where the air turns cool and thin, that vapor gathers into countless droplets and slender ice crystals, and in this unhurried assembly the ordinary marvel of a cloud takes its shape. Sooner or later the sky releases its burden, and the water comes back to the ground as rain, as snow, as mist beating along a leaf in the gray hours that come before morning. Down it travels, threading into rills and brooks and swelling rivers, sliding always toward the lowest ground it can reach, answering the old and steady pull that draws every drop back toward the sea. Some of it sinks instead into the dark soil, seeping between grains of sand and stone to join hidden reserves underground, moving so slowly there that a single passage may outlast whole human lifetimes. Eventually, the wandering meets the ocean once more, that vast gathering basin where the salt and the swell receive it, and there the whole circle rests, ready to lift again with the next warm dawn. Nothing along this route is ever wasted, and nothing is ever truly finished, for each drop is only passing between one form and the next, forever midway on a road that has no end. Hold this quiet fact for a moment. No water anywhere on earth is genuinely new, and none of it is ever really lost, only borrowed for a while and faithfully handed onward. The same rain touching your window has already fallen countless times before tonight, over forests that no longer stand, across seas whose ancient outlines the maps of today would entirely fail to recognize. That very water has been a mountain river, a winter snowbank, a morning fog above the fields, and a wave curling toward some shoreline worn away into forgetting long ages ago. It has passed through living things beyond all counting, drawn upward through roots, carried in the rising sap of trees, and held for a season inside creatures who long ago returned to dust. Perhaps one single droplet completes its whole loop within a matter of days, rising from a warm puddle at noon and falling somewhere else again before the week has fully turned over. Another may sink into the deep ocean or seal itself within the blue heart of a glacier, waiting 1,000 years or 10,000 more before it stirs and rejoins the circle. There is no timetable governing any of this, only the endless taking of turns, each drop finding its own unforced pace through a circulation that began before our oldest stories were ever told. Notice how this makes the water within reach of your hand feel less like something you own and more like a traveler resting briefly in your company before the road calls it away. You are, for this single evening, simply one of the countless places the journey happens to move through, a small and warm waypoint along a route far older than the mountains themselves. By morning it will move on, as it always has and always will, lifting once more toward the clouds to continue the long round it began before anything alive had eyes to watch it. Somewhere in the deep history of everything, long before our sun kindled its first faint light, water was already taking shape in the cold and darkened clouds of gas and dust that wandered, unlit and unhurried, through the wide spaces between the stars. Every molecule of it you swallow tonight is older than the ground beneath your house, older than the ocean it may have come from, and older by far than the great fiery ball that climbs to warm our sky each morning. Consider for a moment where its two ingredients were first born, because their separate stories reach back further than any river or mountain, further even than the rocky world we happen to stand upon tonight. Hydrogen, the lighter half of every water molecule, appeared in the very first few minutes after the universe began, when the whole of creation was impossibly young, impossibly dense, and hotter than anything that has existed since. Oxygen came later, and by a harder road, forged deep inside enormous stars, cooked slowly in their blazing cores across long ages until each of those distant suns finally reached the end of its burning life. When such a star at last died, often in a great outward blaze, it scattered that freshly minted oxygen far across space, seeding the empty void with the second ingredient every water molecule would ever need. Out there upon grains of dust far colder than any winter you have ever known, stray atoms of hydrogen and oxygen settled together and bonded, and the first thin films of ice began to gather, unseen, one atom at a time. Whole clouds of this frozen water floated through the dark reaches of the galaxy for uncounted ages, dim and slow and utterly silent, long before there was ever an earth to hold it or a sun to shine upon it. From one such cloud our own solar system slowly gathered and condensed, and some of that ancient ice survived the fiery making of the planets, folded safely into comets and cold outer dust without ever once melting away. Scientists can read a faint chemical fingerprint held within certain water, a particular ratio of ordinary hydrogen to its heavier cousin deuterium, and that subtle blend marks the water plainly as a relic of the pre-solar age. Because the young sun's fierce warmth would have reshaped and scrambled that delicate ratio, the untouched signature tells researchers with real confidence that a genuine portion of the water on Earth is older than the sun itself. Much of the water that now fills our seas most likely arrived here long ago as a slow, drawn-out rain of icy bodies, of comets and frozen dust falling steadily onto the young and still cooling Earth. Picture those distant travelers now, dark and faintly glittering, carrying whole oceans locked within them across billions of miles of emptiness, before surrendering their frozen cargo to a world that was only just learning how to hold it. So the sea did not simply well up and grow from our own planet alone, but came, at least in part, from the leftover ice of a cosmos immeasurably more ancient than any shore that water would eventually touch. There is a strange comfort in holding this idea a moment, that the plain glass of water resting on your bedside table tonight contains something genuinely measurably older than the first ray of sunlight. Each mouthful you take is a small inheritance handed down from the very beginning of things, atoms that waited out in the darkness between the stars for an almost unimaginable stretch of time before ever reaching you. You are, in the plainest and most literal sense there is, sipping the long melted remnants of the early universe, gathered now and held together in a shape as humble and familiar as a single falling raindrop. Rest now with the sheer wonder of it, that this most ordinary substance carries within it a history far older than the sun, and that some small measure of that history is moving through you at this very moment. Long before anyone thought to look outward, we imagined Earth as the lonely blue exception, the single water world adrift among dry and lifeless stones, circling its star in solitude, while the other planets stayed barren and parched. That old picture, it turns out, was far too small and far too lonely, for the same familiar liquid that fills the glass on your bedside table is scattered with surprising generosity across the outer reaches of our solar system. Consider the many moons of Jupiter and Saturn, small frozen worlds wrapped in thick shells of ice, each one seeming from the outside as barren, airless, and bitterly cold as anything you could ever imagine finding out there. Beneath those pale crusts, though something genuinely remarkable lies hidden, whole oceans of liquid water sealed away in perpetual darkness, held far below the freezing point you might expect and never once glimpsed from the surface above. On Europa, one of the great moons of Jupiter, a global sea most likely rolls and turns beneath a rind of ice many kilometers thick, never once touched by sunlight and utterly walled off from the sky. You might well wonder how any ocean could stay liquid so far from the warmth of the sun, out where the surface temperatures plunge to well over 100 degrees below freezing, and the light is thin and faint. The answer lies in a slow and unrelenting squeezing, for as these moons swing in their long orbits around their giant planets, the shifting pull of gravity stretches, flexes, and kneads their deep interiors without pause. This ceaseless tidal working generates real heat deep inside the rock and ice, and that steady inner warmth, welling up from friction alone, is enough to keep an entire buried sea from ever hardening into solid ice. Saturn's little moon Enceladus does something even more startling than merely hiding a sea, venting tall plumes of water vapor and glittering ice through long cracks near its southern pole, spraying them far out into open space. Those shimmering jets are the clearest sign we yet have that a genuine ocean sloshes and stirs beneath the moon's frozen shell, leaking slowly upward through the fractures and escaping into the emptiness hanging overhead. Some of these buried seas may hold more water than all the oceans of Earth combined, vast dark reservoirs of it tucked away inside worlds far smaller than our own, unseen and unlit through the whole of their history. Comets add their own strange chapter to this story, wandering mountains of ancient ice that have circled the distant sun on enormous looping paths ever since the solar system first gathered itself out of dust and gas. When one of these icy travelers swings close to the sun at last, a little of its frozen water turns straight to vapor without ever melting, streaming out behind it into that famous long and glowing tail. Water hides closer to home as well, bound not in open seas but locked deep within the very stone of Earth's mantle, hundreds of kilometers beneath your feet, where no drill has ever reached to find it. There, immense pressures press hydrogen and oxygen into the crystal structure of certain deep minerals, so that a quantity of water rivaling all the surface oceans may lie sealed inside solid rock, neither flowing nor pooling anywhere. Piece all of these scattered clues together, and a lovely truth slowly emerges, that our planet is not some rare and singular oasis after all, but only one water world among many in a surprisingly wet and generous cosmos. From the hidden seas beneath icy moons, to the frozen hearts of distant comets, to the dampness woven all through buried stone, this one simple molecule turns out to be among the commonest treasures the whole universe has to offer. Carry into sleep, then, the strange comfort of knowing that the same substance filling those countless hidden oceans buried and unseen across the solar system is the very stuff that flows warm and familiar through you tonight. High in the mountains, where each winter's snow falls faster than the summer's sun can melt it away, the fallen flakes pile deeper year upon year, and beneath their own steadily accumulating weight they compress little by little into dense, glassy ice. Layer upon layer, that ancient snow is pressed and squeezed until nearly all the air is driven from between its crystals, and what began as a soft, feathery blanket gradually becomes a solid body of ice hundreds of feet thick. Such an enormous mass grows far too heavy to remain where it first gathered, and so it begins to move, creeping steadily downhill under the constant, unresisting pull of its own tremendous weight. A glacier is, in the truest sense of the word, a river made of ice, flowing not in hours but across years and centuries, its progress measured in inches a day rather than miles an hour. Picture the sheer strangeness of that motion, a substance we know as brittle and breakable somehow bending, oozing, and sliding down the slope as though it had become a slow, thickened kind of honey. Deep within the glacier, where the pressure of all that overlying ice grows truly immense, the crystals themselves begin to deform, gliding across one another so the whole body flows onward without ever cracking apart. Nearer the surface, though, The ice stays cold and rigid and unyielding, and where the glacier bends over a steep rocky ledge, it fractures into deep crevasses that split the frozen river open along their length. So a glacier lives a curious double life, rigid and shattering at its surface, yielding and creeping in its depths, caught somewhere between the solid and the liquid in a way few other things on Earth can be. As it grinds ever forward, the underside of the ice plucks loose boulders from the ground and clutches them tight, dragging this heavy cargo of broken stone along the bedrock like an immense unhurried sheet of sandpaper. Over unimaginable ages, that scouring load carves the very land itself, gouging out the wide, rounded valleys and deep hollows that a glacier leaves behind long after the ice that shaped them has melted entirely away. Notice how a river of running water cuts a narrow V down into the hills, while a river of ice grinds out a broad, smooth-sided U, a signature you can read written across whole mountain ranges. When at last the flowing ice reaches lower, warmer ground, its leading edge melts away as fast as fresh ice arrives from behind, and there it sets down its long-carried burden of rubble in sprawling ridges. Consider the long journey of a single crystal now resting at the glacier's foot, and how it may first have fallen as a snowflake upon some distant windswept summit 1,000 years or more ago. Century after century, that single flake was buried, compressed, and carried steadily downward, an unhurried traveler borne along on ice that moved far slower than the eye could ever follow. The ice arriving at the melting edge today may hold locked within it snow that first settled long before cities were built, before writing was invented, before much of what we now call history had even begun. In the oldest and deepest glaciers, bubbles of genuinely ancient air stay trapped between the crystals, tiny sealed pockets of a long-vanished sky preserved for many thousands of years within the slow-moving frozen current. Picture that immense, unhurried procession as you lie here, whole valleys of ice sliding toward the sea across many lifetimes, grinding great mountains grain by grain into the beds and basins of the world. Somewhere tonight, even as you settle toward sleep, a glacier is still moving, a little further with each passing hour, carrying its ancient snow toward a rest it has been approaching since long before you were born. Long before the first gray light arrives at the window, the air lying close against the ground carries far more water than you would ever guess, held there invisibly as vapor that no eye can see and no hand can feel. On a clear and windless night, warmth radiates freely upward from every blade of grass, every fence rail, and every pane of glass, and those exposed surfaces cool a little below the temperature of the air that rests against them. As each cooling surface chills the thin layer of air pressed just above it, that air is drawn toward a threshold where it can no longer hold all the water it had been carrying hidden away in the form of unseen vapor. Scientists call this crossing the dew point, the exact temperature at which the air becomes saturated and can hold no more, so its invisible moisture begins to gather itself back into small drops of liquid water. Beyond that point, the molecules of water that had been wandering apart through the open air slow their restless motion, drift downward, and settle together upon whatever cool surface they happen to touch first. Blade by blade across a darkened lawn, they collect into countless small beads, each droplet pulled round and whole by the same cohesion that draws water inward toward itself wherever it is left free to do so. Look closely at a spider's web strung with dew in the first light of daybreak, and you will find it hung with a row of tiny glistening lenses, every bead a single drop condensed straight out of the night air. None of this water fell from any cloud above, for not a single drop of rain touched the ground while you were sleeping, and the sky stayed clear and open from dusk until the pale return of morning. The moisture had been present the whole long while, dissolved through the darkness as vapor and mingled invisibly with the air, awaiting only the chill of the cooling surfaces that would finally coax it out of hiding. When the cooling deepens further and a surface falls below the freezing mark, the water vapor skips over the liquid step altogether and knits itself directly into the delicate white crystals we know as frost. This direct passage from gas straight to solid, without any pause as liquid in between, is named deposition, a mirror image of the way ice can turn back into vapor without ever first melting into a pool of water. Along the cold edges of a leaf or a window pane, frost grows outward in delicate feathered spikes and branching fronds like tiny ferns, each slender arm following the same six-sided geometry that ice always seems to prefer. Whether you wake to find soft beads of dew or a lacework of frozen crystals depends on no more than a single degree or two on whether the cold that night slipped across the line where water turns to ice. Both of these forms share one humble and ordinary origin, the everyday water riding unseen within the air itself, drawn down out of the dark and made suddenly visible by nothing grander than a slow fall in temperature. Notice how dew and frost gather most generously in the low hollows and open fields, in just those places where the coldest air settles and pools and where surfaces radiate their warmth away most freely into a cloudless sky. A blanket of cloud, by contrast, traps that escaping heat and holds the surfaces below a good deal warmer, which is the simple reason a gray and overcast night so often leaves the morning grass entirely dry. Dawn asks nothing of the world to bring any of this about, and simply draws back the darkness to reveal what the long night had been assembling in silence, drop by drop, out of the seeming emptiness of the air. Carry with you into sleep the image of that silver freshness spread across the fields at first light, a small daily gift of water gathered by the world out of nothing but the dark and cooling hours. Everything you have followed so far through this long night lives inside you as well, for you yourself are built mostly from the very water we have spent these hours describing, the same rule-bending liquid moving through your warmth right now. Roughly 2/3 of your body is water, woven through your blood, pooled behind your eyes as tears, cushioning your joints, and filling the crowded interior of every single living cell you carry from head to foot. Within each of those countless cells lies a warm inner sea, and it holds the delicate molecules of life in suspension, letting them float close, meet, fold into shape, and carry out the work that keeps you alive. Your blood itself is largely water, carrying its precious cargo of oxygen, salt, and sugar to every corner of you, a private inland ocean circulating through your body with each steady beat of your heart. When you weep at something tender, or when you sweat through the heat of a long summer afternoon, you are letting a little of that ancient substance slip out of you and return to the wider world outside. Consider that the water threaded through your tissues tonight was never truly made to be yours, for it is only passing through, borrowed for a while, lingering in your warmth before it moves on to somewhere else entirely. Long before it ever belonged to you, some of it rolled as a gray ocean swell, rose as vapor into a bright and empty sky, and fell again as rain onto distant hills you will never see. One day, in some season far beyond this present one, those very same molecules will leave you behind and slip back out toward river and cloud and open sea, carrying on their long travels well after you are gone. You are less an owner of this water than a passing shape it briefly borrows and fills, a living vessel through which the oldest liquid on all of Earth keeps traveling on its long, unhurried way. The identical substance that fills the deep ocean trenches and floats as pale ice upon far northern lakes is, at this very moment, moving through the warmth of your own body and threading between your cells. Notice how strange and how lovely that thought becomes as you lie here. The far-off seas and you yourself are fashioned from precisely the same restless, rule-bending stuff, obeying one physics from horizon to heartbeat. Each molecule within you bends at that same tender angle we traced, forms and lets go of the same fleeting hydrogen bonds, and dissolves the same salts and sugars we marveled at together across all these long chapters. There is nothing separate or set apart about the water moving in your veins tonight, for it obeys exactly the same physics that shapes falling rain, grinding glacier, morning dew, and the vast and open ocean beyond. Let yourself feel held, then, by a substance far older even than your own name, one that has already been countless things across the ages and will go on to be countless more in all the years that follow. Breathe out slowly and know that the faint moisture riding on your breath rejoins the air of the room, ready to condense somewhere far away in the world as another cool morning's mist or a bead of dew. You are, in the truest and most literal sense there is, a small warm tide, a portion of the planet's ancient water briefly gathered up and given the shape and name of a single person. Feel the ancient seas continuing on inside you, unhurried and familiar and utterly ordinary, the very same water that once cradled the first fragile living things, now cradling you here in the dark tonight. Rest here a while in that deep kinship, aware that the whole strangeness of water is not something far away out in the oceans, but is flowing tenderly and faithfully through you, even as you begin to settle into rest tonight. Here at the end of our long, unhurried night together, let everything we noticed loosen its hold and slip away, the way a long-held breath finally releases itself and the chest sinks lower than before. You need remember none of it, for each strange marvel we met will go on being true, whether or not any mind stays awake to hold it. It's plain physics needing no witness to keep working through the dark. Somewhere above a dark lake, a thin lid of ice is floating on the very water it came from, buoyant and light, riding higher than the dark depths it shelters, guarding the living warmth held below. Picture that floating roof once more, then let the image blur at its edges and slide away into the dark, taking its cold along with it as your own shoulders grow heavy and sink into the bed. Rain that fell 100 years ago is rising again as invisible vapor tonight, circling on through cloud and river and open sea in a slow wheel that has never once in all that time stopped turning. That same unbroken turning has carried the very same water around and around for billions of years, and it asks nothing of you now but to loosen your grip on the day and let it go on turning without you. Within any resting glass on any darkened bedside table, the molecules are still trading their fleeting handholds, breaking apart and reforming trillions of times over in a restless, invisible motion that never once tires or asks for rest. Even now that ceaseless inner shimmer goes on beneath a perfect outward stillness, a hidden dance you are free to simply set down and stop watching altogether as the room dims and the walls fade further away. Remember, too, that a great share of what you are is this very same substance, moving through you and cushioning every cell, warm and unremarkable, and, for this little while at least, entirely yours. Feel that inward tide grow level and even, the way the surface of a pool comes back to smoothness once the last ripple has spread out to the banks and finally spent itself against them. No lesson waits for you here, nothing you must hold or carry forward into tomorrow, only the slow permission to let each remaining thought thin out and dissolve the way sugar disappears into a cup of warm tea. Let the bent little molecule, the six-fold order of ice, the sap climbing its tall trees, and the taut silver skin of the pond all fade together now into one dim and wordless blur behind your eyes. Sink a small measure lower now, down past the images and the facts, and the very words that carried them, toward the silent place where thinking loosens its hold and the body simply floats free. Every wonder we touch tonight will still be waiting unchanged and entirely true on any morning you might care to return to it, so there is nothing here to keep and nothing to lose. Down and down you go, sinking the way a single leaf settles through dark and shadowed water, turning over once unhurried, meeting no resistance anywhere, and finding at last its own natural resting depth. Around you the whole world grows dim and warm and blessedly ordinary, softening at every edge, and the vast strangeness of water we followed all night asks only this of you, that you rest easily inside it. Let this be the very last thought before sleep, weightless as a breath of vapor, endless as the turning cycle, and near as the same familiar water moving warm within your own slowly rising chest. Sink now all the way down into that deep and welcoming warmth, and sleep well. Good night, and then good night once again, softly and completely, all the way down into the dark.